The equation of a curve is y equals e to the power of minus x squared. We want to find dy dx. Now, we need to look at the derivative of e to the power of x with respect to x. Well, we know that that's just e to the power of x. It's the only function whose derivative is itself. So you'll see that in tables. But the power here is more complicated than x. It's minus x squared. So we have to use the chain rule. So when we differentiate y equals e to the power of something, we just copy it down. And we then multiply by the derivative of the power. The derivative of minus x squared is minus 2x. So that's the chain rule. So I explained that in an earlier video. Well, I explained how it works out by letting u equal minus x squared and then calculating dy du. This would be dy du here, and then du dx. In part 2 we want to find the coordinates of the turning point of the curve. Now to find a turning point of the curve we put dy dx equal to 0 because dy dx is the slope of a tangent to the curve. So here I have a graph of the curve. Of course you don't really need to know the graph to actually do this question, but you can see that at x equals 0 we have a turning point because the tangent to the graph at x equals 0 is a horizontal line, which means its slope is 0. So dy dx is the slope of a tangent. We put it equal to 0 and we solve, and hopefully we will get x equals 0. So we put minus 2x times e to the minus x squared equal to 0, and we solve this equation. Well, we can look at this equation in two ways. We have a product of functions here giving 0. The only way that a product of functions or quantities gives 0 is if either one of them is 0. So that means either x is 0 or we have e to the minus x squared equals 0. Now the only way that e to the power of minus x squared can equal 0 is when x is either plus or minus infinity. So if we take a very large positive value of x, an infinitely large positive value of x, then you will see that the tangent is just the x-axis. The tangent to the curve is actually the x-axis. This curve never crosses the positive x-axis. It actually keeps on approaching the positive x-axis but never reaches it. It looks like it's reaching it here at 2, but it doesn't actually. In reality, this curve approaches the positive x-axis asymptotically. So the x-axis is an asymptote. So at plus infinity you could say we have a turning point, but it's not a true turning point because plus infinity is not a number. Similarly for minus infinity, for a very large negative value of x, or an infinitely large negative value of x, e to the minus x squared will be 0. Now why is that? Why is e to the minus x squared 0 when x is plus or minus infinity? Well, we can write e to the minus x squared as 1 over e to the plus x squared. That's the meaning of the negative power. And when x is infinitely large, then 1 over e to the power of x squared is effectively 0. It's really that the case that the limit of e to the minus x squared as x tends towards plus or minus infinity is 0. It's a limiting case. So we're not talking about true turning points here. So we can just disregard all of this and say that the turning point is at x equals 0. Now we want the coordinates of the turning point of the curve. So we know that at x equals 0 we have a turning point, dy dx is 0. But we want the y value of the turning point. The x value is 0. What's the y value? Well, we just need the equation of the curve. So we want the coordinates of this point here. So the x value is 0. So the y value is got by going to the equation of the curve, which is y equals e to the power minus x squared, and plugging 0 in for x. So we get e to the power minus 0 squared. Well, that's just e to the power of 0, and e to the power of 0 is 1. Any number to the power of 0 is 1. So the coordinates of the turning point is 0, 1. Now, by the way, this is the only turning point, because as I said already, plus or minus infinity, the value, the point on the curve at when x is plus or minus infinity are not true turning points. Well, basically, the tangent may be horizontal at x equals plus or minus infinity, but the curve doesn't actually turn again, even though the tangent is horizontal. So we ignore that case. So there's only one truth. There's only one turning point, essentially, and it's at 0, 1. It's this point here. In part 3, we want to determine whether this turning point is a local maximum or a local minimum. Well, we can see from the graph that it's a local maximum. But let's suppose that we don't have the graph at our disposal. What we could do is look at values of x on either side of the x value of the turning point. So this is one method for doing it. The other method involves the second derivative, but I just want to go through this method. So let's take values on either side of x equals 0. So we take minus 0.1 and let's take 0.1. What we do is we calculate y for each of these two values, and if the y values we get are less than 1, then this turning point must be a local max. So let's evaluate y when x equals minus 0.1. So that's a value close to 0, just to the left of 0. So we plug minus 0.01 in for x in the equation of the curve. So we're going to get e to the minus bracket minus 0.1 squared. Now minus 0.1 squared is plus 0.01, and then we have a minus sign, so we want e to the power of minus 0.01. So you see we get 0.99. We do indeed get a number that's less than 1. Of course, we know when x is 0, we get y equals 1. Now, what about x equals plus 0.1? That's this value here. Will we get a value that's less than 1? So what we want is 0.01. Well, we want minus 0.01. That's minus 0.1 squared. See, we get 0.99. We actually get the same value as this value here. This curve is actually symmetrical about the y-axis. So you could illustrate your answer like this. You can show the turning point at 0, 1. And you could show the point with coordinate 0.1.99, which is below this point, and the point with coordinates minus 0.1, 0.99. As a matter of fact, you probably only need to work out one of these 2 points, because if there's a turning point at 0, 1, then if you get a point that's lower than 0, 1 at 0.1, then this can only be a local maximum. Although it's possible actually that you could have a curve like this. It's possible to have a horizontal tangent where you have what's called a saddle point at 0, 1. So 0, 1 might not necessarily be a local max or min. Okay, if the curve is this, say, red curve, then it's possible that the tangent at 0, 1 is still a horizontal line. It would actually be a horizontal line that would cut through the curve, but nevertheless it's a horizontal line. So in order to rule out that situation, you really want to pick 2 points on either side of your turning point, and it turns out for both of these points are below the turning point, so we must have a local maximum. Now the other way to do this is to use what's called a second derivative test, which I explained in a previous video. It's based on the idea that the derivative of this function is decreasing at this point here. Well, the second derivative, I should say, is decreasing, is negative at this point. The first derivatives are decreasing in the neighborhood of x equals 0. At x equals 0, the first derivative is of course 0, so we have a turning point, but the slopes of the tangents are decreasing for values in the neighborhood of 0. And if the first derivative is decreasing, it means that the second derivative is negative at 0. So we need to look at the second derivative at x equals 0. Now, to get the second derivative, we need to differentiate this, and this is a product of functions. So you can think of it as u times v. So we have u, the first function, times the derivative of the second function. Well, if we work out dv dx, we get minus 2x e to the minus x squared. It's just the same as differentiating this, which is this. So this is u times dv dx plus v, which is e to the minus x squared, times du dx. If we differentiate minus 2x, we get minus 2. What we need to do is evaluate the second derivative at the turning point. We need to evaluate it at x equals 0 and see if it's positive or negative. So we plug 0 in for x. Well, when we plug 0 in for x here, we get minus 2 times 0 times, minus 2 times 0, e to the minus 0 squared. Well, that's going to go out because we've 0 in this product here. So this term will disappear. But when we plug 0 in here, we get e to the power of 0 times minus 2. So we get 1 times minus 2, which is minus 2. So we get a negative result. So that tells us that the turning point, 0, 1, is the coordinates of the turning point, is a local maximum. As I explained in a previous video, the second derivative, d2y dx2, is the rate of change of dy dx with respect to x. In other words, it's the rate of change of the slope of the curve, or the slopes of tangents to the curve, as x increases. And you can see that those at a local max, in the neighborhood of a local maximum, those the tangents are decreasing in slope. See, this tangent here is a positive slope, then the slope is 0, then the slope is negative. So the rate of change of the slopes of tangents is negative, but the rate of change of slopes of tangents is exactly this here. If this value is positive, then we would have a local minimum. As an aside, I'll just mention that y equals e to the minus x squared is called an even function. By an even function, I mean that it is symmetric about the y-axis. Okay, so if you take the value of y at, say, x equals 1, and the value of y at x equals minus 1, you'll get the same values. If you plug 1 in for x, you get e to the minus 1 squared. Well, that's just e to the power minus 1. So the value of y at 1 is e to the power minus 1. So this is a point with coordinates 1 comma e to the power minus 1, or 1 over e. E to the power minus 1 is 1 over e. It's 1 over 2.7 roughly. But of course, if you plug minus 1 in, it makes no difference, because when you square minus 1, you're going to get plus 1 here. So you're going to get the same value at the negative x value. So if x is 1, the value you get at minus 1 will be the same. So in other words, the value of the function at minus x is the same as the value of the function at x. Or if you like, the value of f at minus x is the same as the value of f at x, if we're using f for our function.